Welcome back, students. So today in this lecture, we'll start talking about yield criterion. So if you remember uniaxial tensile test, you would know that we have something called as yield strength or yield stress. So at that particular stress value, the material transits from elastic region to plastic region. What would happen if the stress state was not uniaxial in nature? It would be actually a lot more difficult. It is not straightforward to understand when the plastic deformation or the plasticity in the material would begin. We will show that with an example, and hence we need some criterion which would include the overall stress state to define whether the material is still in the elastic region or it has transited into the plastic deformation zone. So let's begin. So this yield criterion you would see is covered in chapter 6 by Hosford and Cadell. So the first important point to understand is that deformation is usually not uniaxial in nature. So let's say we have a body like this, where whatever stress state we define remains uniform throughout. Okay, so let's say it is initially under uniaxial condition, and it is given that the yield strength of this material is 200 megapascal. Okay, now if you are applying a uniaxial stress like this, and let's say it is 220 megapascal. The question is, will the material yield? And the emphatic answer is yes. It will yield. In uniaxial, we know the overall stress of 200 megapascal has been exceeded. Now let's look at a little different example. Again, we have the same body, but now it is not under uniaxial stress state. So, but this direction, we would still apply 220 megapascal. But okay, so the drawing may be a little misleading. So when I say it is basically on the opposite faces, okay, so that much should be clear to you. Now we are also applying a yield stress of 150 megapascal along this. And yes, I didn't mention it explicitly, but you can assume plane stress condition for both these. Now again, the question is, will it yield? So it looks like it should, because we have applied the same stress. In fact, we are applying more than that stress. So the first instinct would be to say yes, but the answer is no. Actually, and when you draw the Mohr circle, this will become even more clear. But for now, I will just draw it like this. So for the first state where we have uniaxial under this condition, which means that on the other side, which again, assuming plane stress condition, here it is 0. So the overall stress state can be defined like this by using this Mohr circle. So here it was 220, here it was 0. And therefore, we know it will yield. Now in the second condition, what is happening is that the stress state on this direction is still 220, but on the other direction, it is now 150. Now you see that the size of the circle has grown smaller. Although its position is still, the rightmost position is still at 220, but the overall size of the circle has become smaller. And only later we would see that it is the size of the circle that determines whether yielding will take place or not. Not the actual value. So you see, it must have come as a surprise to most of you, because what this means theoretically, that even if you make it 500 or 1000, but as long as the size of the circle, meaning the other side, you are still applying 900. So 900 and 1000, these are the two stresses you are applying, then the material will not yield. That is what this condition, or this will something condition that we'll define later on. But in general, this is what the yielding means. And that is how multi-axial stress condition can change the overall scenario. And that is why we need to have a good understanding of overall stress state and not just one or unidirectional stress state. Okay, having said that, now let's look at what are the places where we see multi-axial stress in nature. So not in nature, in process. So let's look at some of these processes. Most of the, actually I should say industrial process, are multi-axial in nature. For example, if we talk about rolling, then what is the rate of stress? It is biaxial compression. If we talk about swedging, this is also biaxial compression. If we talk about forging, then it is triaxial compression. If we talk about extrusion, then again it is triaxial compression. And these are some of the most common ones. But if you keep on listing even other industrial processes, forming processes, you would see that all of them are multi-axial in nature. So what is it that we understand from this? That we need to have a formulation which can take into account this multi-axial state of stress. We need to define yielding in a holistic way. That is the first thing. What do we mean by holistic way? Which includes the overall stress state. Okay, so if we were to put it mathematically, then we can write it like this, that F sigma x, sigma y, sigma z, tau xy, tau yz, tau zx. Some function of this, when this reaches some constant value, that is when the material starts to yield. So that is our objective, or that is what we understand, get understanding from the above example, that this is what will be needed. And it looks like it would be a very gigantic or humongous task. but it is not really so. As you would see, it turns out to be a lot more simpler than what this equation states. First of all, if you look at the same thing, if it were to be written in terms of principal stresses, then in terms of principal stresses, we would write as so when we have principal stresses, obviously we don't have shear stresses, and therefore it is just a function of sigma 1, sigma 2, sigma 3. And since these two constants would not be same, so let me put a prime over here to just to distinguish that this is a different constant and this is a different constant. Unless someone gets confused that both the equations will yield the same constant. That's not the case. Now, what are some certain assumptions that we need to make, particularly from the point of view that we have isotropic material, and what are our observations which must be fulfilled if we define any yielding criterion? So what are those assumptions? So let's list out those. So we are assuming isotropic material, okay, meaning a polycrystalline material which has uniform properties in all directions. First of all, magnitude of mean normal stress does not influence yielding. Okay, this is an observation which is very valid and well known, that if you increase the magnitude of mean stress, then the yield strength of the material does not change. For example, if you are doing the yield test in air versus you take the whole thing, the whole setup inside water where there is hydrostatic stress, and you keep going deeper and deeper, so hydrostatic stress keeps increasing, but the yield strength of the material does not change. This is the understanding, and that therefore your criterion must be able to fulfill this. And if you take the stress tensor, then what it means is that you can take away the sigma m, which is sigma xx plus sigma yy plus sigma zz by 3 from this factor, this quantity away from this, deduct this from the stress tensor, and the quantity that is left behind would still define the same yield criterion or the yield strength of the material. No Bossinger effect. Now in usual material, you would see that there is very little or negligible difference whether you are applying tension or compression. If you go to the bond property, then we know that it is a little bit asymmetric, but the amount of strength that we are applying in the range that we are working on, in that range, it is almost U-shaped, which is symmetric. And hence, the Bossinger, what it says is that there should be no Bossinger effect, meaning the stress in the tension should produce the same amount of strain as the stress in the compression. Yield strength in tension is to yield strength in another important criterion is that the volume of the material should not change. So there should be a constancy of volume because it is plastic deformation. So the overall volume must not change. and it is expressed as constancy of volume, which in other words means that the Poisson ratio nu should be equal to 0.5. So these are some important assumptions that must be satisfied if we are to set up a equation or set up a model mathematical formulation to define the yielding of the material. Now, in this respect, let's visit one topic that would be very helpful for us to understand the overall yielding condition, and that is principal shear stress. So you remember the principal stresses. We had three principal stresses: sigma 1, sigma 2, and sigma 3. And usually we know that sigma 1 is greater than sigma 2 is greater than sigma 3. Now let's say this is a body where sigma 1 and sigma 3 are sigma 1 and sigma 2 are acting. So this is sigma 1 like this, and this is sigma 2. Then you can easily show that the plane at 45 degree would be the planes where maximum shear stress in this particular plane. So if you are assuming a plane stress condition, in this particular plane, that would be the maximum. So that particular plane would have maximum shear stress, and that would be given by, I'm giving the name tau 3 right now, because as you would see, it would be the lower, one of the lower ones. So we will say sigma 1, and you can easily show that it will be sigma 1 minus sigma 2 by 2. The other condition that we can have, where this is sigma 1, and now let's, in this particular plane, so this is, so there is sigma 3 in this direction. So sigma 1 is in this direction and sigma 3 is in this direction. So again, for this particular plane, the maximum shear stress would be along these orange planes, which are at 45 degrees. And since sigma 3 and sigma 1 are the maxima, minima and maxima, so sigma 1 is the maximum, sigma 3 is the minimum. So whatever tau we get here, so just put tau, and this is sigma 1 minus sigma 3 by 2. But since these two are the extrema, therefore this will also be the largest value, and therefore this will be tau 1 or equal to tau max. Okay, now, so basically this is not in the terms of shear stresses, it is not termed according to the highest and lowest. This is 1 and 3, so this is tau 2. And now over here we have sigma 3, sigma 2, so here we have tau 1 equal to sigma 2 minus sigma 3 by 2. And these are the maximum shear stresses in that particular plane. So this is the maximum shear stress in the plane of sigma 1, 2, which is given by tau 3 equal to sigma 1 minus 2. If you take at any other plane, then it would be lower than this value. Similarly, for the plane in the sigma 1, sigma 3 plane, this is the maximum shear stress. In fact, this happens to be the highest shear stress that you can get for this stress state. And for this plane, sigma 2 and sigma 3 plane, tau 1, this is the highest shear stress. And therefore, these are called the principal shear stresses. And what we see is that principal shear stresses can be expressed in terms of principal stresses, which was sigma 1 and sigma 2 and sigma 3. Okay, so now that we are comfortable with this concept of principal shear stresses, and we know the relation and how to get the principal shear stresses, which is in terms of the principal stresses, sigma 1, sigma 2, sigma 3. Now let's move on to another important, or basically let's now look at the stress tensor quantity. And then you would be able to start getting an idea on how to define that criterion. Now we know that stress is a matrix or a tensor. So it has 9 quantities, and it is sigma xx, sigma xy, sigma xz, now this stress tensor, or the overall components of the stress, can actually be divided into 2 major components. What are those 2 major components? Those 2 major components are hydrostatic stress and deviatoric or deviator stress. Hydrostatic stress is basically nothing but the mean stress. So this is also called as mean stress. It involves only pure tension or compression. On the other hand, deviatoric stress, it represents shear stress. We will be able to dissociate the 2 components very soon. First, just let's go through the terminologies and what they mean. So this represents shear stresses. Now, if you remember in the bond model, when you are doing just tension or compression, you are basically only, what it yields is only the elastic deformation of the material. So hydrostatic stress involves only elastic changes. On the other hand, shear, which is basically shearing of the plane of atoms, and this stress is what leads to the breaking of the bond, and hence generation of the dislocations, as a concept that we will visit very soon. So this is the one which actually leads to or causes plastic deformation. So this is important for plastic deformation. Now coming to the definition. So sigma m, or the mean stress, which is also the hydrostatic stress, like we said, is nothing but sigma x plus sigma y plus sigma z by 3. And if it were to be expressed in principal stresses, then it will be sigma 1 plus sigma 2 plus sigma 3 by 3. So this is the hydrostatic stress component. Now, if you take away this component, which is from the diagonal component sigma xx, sigma yy, and sigma zz, if we take away this component from a general stress matrix, so this is the stress general stress matrix, and these are the sigma xx, sigma yy, sigma zz. So if you subtract, then this is where these quantities will get subtracted, and what you are left with is this one. So this is the deviator stress. So clearly this one was obtained by subtracting this, and therefore the overall stress is nothing but sum of sigma m plus sigma ij prime. Sigma ij prime is what? Our deviator stress. So the hydrostatic stress plus the deviator stress. So this stress quantity is clearly composed of hydrostatic stress and deviator stress, but that is not all. What we will see again now is that this deviator stress is actually composed only of shear stresses. How? Let's see. Now we have this quantity. So these are purely shear quantities, tau. Now the only ones that we are not able to recognize as shear are these quantities: sigma x, 2 sigma x minus sigma y. Let's call it sigma x prime, which is equal to 2 sigma x minus sigma y minus sigma z by 3. But this can also be written as sigma x minus sigma y plus sigma x minus sigma z by 3. So this is clearly a shear stress quantity. And thus, if you look at all these terms, this one, and this one, all of these are basically nothing but shear stress quantity. And therefore, deviator stress is composed only of so if we were to write it in terms of principal stresses, then this would become like this. Which is equivalent to which is equivalent to 2 by 3. This is tau 2, this is tau 3, this is tau 3 plus tau 2. Therefore, if you were to write in terms of principal stresses again, you would see that it will translate to principal shear stresses. The deviator stress will transform into a stress matrix with only the principal shear stresses. And therefore, it is now clearly established that the deviator stress is composed only of the shear stresses. Now, with this understanding, we are now clear that the plastic deformation that takes place in the material takes place only when there is a shear stress, and the shear stress is basically has to be some function of shear stress. So the shear stress the combination of the shear stresses must reach some value when the deformation or plastic deformation can be said to have begun. And therefore, based on our understanding, we can say that the criterion must fulfill the following requirements. What are these requirements? Let's see. Since deformation occurs by shear stress, so earlier we said that it should be some function of sigma 1, sigma 2, sigma 3, or sigma x, sigma y, sigma z. But now we can refine it further. Now we can say, since deformation occurs by shear criterion must be a function of Stressdeviator. So Stressdeviator represents the overall stress state in terms of shear stresses alone. And we know that this is what will cause the plastic deformation, not the mean stresses. In fact, we have given that example that if you change the mean stress either plus or minus, it does not change the yielding condition. So this is the only stress state, the only component of the stress state which will define the yielding is the deviator. Therefore, we can now say that F as a function of sigma 2 minus sigma 3 minus sigma 1. This is in terms of principal stresses. Similarly, you can also get it in terms of other or normal stresses. This should reach some value C. So this is our more fine-tuned equation. This is the formalism of the mathematical equation that we should obtain. And now, based on this, we are now confirmed what I said earlier with that example, that it is size of the mode circle does not matter. And not position should determine yielding. Now that we are saying that the mean stresses should not cause change in the yielding, then mathematically, how do we say that? So if the condition that sigma 1, sigma 2, sigma 3, it is a combination of stress state that causes yielding, then sigma 1 prime equal to sigma 1 plus or maybe minus, whatever you do, a mean stress value or any other stress value, in fact. Sigma 2 prime equal to sigma 2 plus minus sigma m. This should also lead to yielding. So this is another condition that it must satisfy. If the above what we have said, what we have derived earlier is true, then this must also be true. Now, if we want to get a little bit more understanding about how the criterion should look like, then we can also look at our isotropic material. Now, if you are looking at the isotropic material and change the orientation, and then you get some stress state, and then you derive the yielding condition, then whether it is yielding or not, that condition should not change just because you have changed the axis. Therefore, the yielding criterion should be independent of choice of axis. And hence, this something which is independent of the choice of axis is invariant. And therefore, we can also say that this criterion must be some function of invariance. And this time not the invariant of the original stress tensor, but now that also we have described that only the deviator contains the shear stresses. So invariants of the deviator stress component. So this part has helped us jot down or finalize our criterion to a great deal. As you would see that this particular statement can help us get down to a very meaningful yielding criterion. That is just one of the yielding criterion, and the yielding criterions are not universal. It can change from material to material, only that it must satisfy those conditions that we have described earlier. And the one that is based on this one, just based on the overall, which is able to satisfy all of these, is what is called as von Mises criterion. And this one is what helps us boil down to the final equation for the von Mises criterion. Even otherwise, there is still another one which satisfies up to this one, all these one. It need not be directly a relation of the invariants, but it does satisfy all the other conditions, and that is a Tresca criterion. Actually, it will also satisfy the last one, only that it is a much more simpler form of the equation, and this one will be directly utilized from the invariants of the deviator stress. And this one is a lot more simpler one, although it satisfies all the conditions. In fact, any valid yielding criterion must satisfy all these conditions. So we will look at the derivation of, not the derivation, but now that we have this equation, we will be able to jot down the von Mises criterion, and also based on our primary understanding, we will be able to jot down the Tresca criterion, and then we will see whether they satisfy all the conditions and how they relate with the yield strength and the shear strength of the material. And along with that, we will also look at another yielding criterion, which is the Rankine criterion. Although it does not satisfy all this, and we will see which of the ones it does not satisfy. So with the introduction of these three yielding criterions and the conditions, we will end this lecture over here. And we will, in the next few lectures, we will go through these different criterions. Thank you.